Hi, welcome to our 37th lecture in combinatorics. Today we'll start by giving an example of how the Hungarian algorithm works. So let's recall that the Hungarian algorithm is used to find a maximum weight transversal in a square matrix n by n. So we have this matrix W, and we have to choose one entry from each row in each column such that the sum of these entries is maximum over all possible such transversals. Now, we saw last time that we introduced the notion of UV cover, and we showed that the weight of any transversal is at most the cost of a cover. And if we have equality, then the transversal is going to have a maximum weight, and the cover will have minimum cost. So let's see how the algorithm works on an example. So what we do, let's say we have this matrix 5 by 5 W, and we can start with a cover. Let's say UI is a maximum entry in row I, and VJ is 0. So clearly the condition from the condition of a cover. So as you recall, UV cover means that Wij has to be at most UI plus VJ for every Ij between 1 and n. That condition is satisfied. So then we look at those entries where we actually have equality, and we form what is called the equality graph. This gamma UV, let's call it equality bipartite graph. And this is a bipartite graph, which is 5 by 5. The one partite set corresponds to the rows of the matrix, and the other partite sets correspond to the columns of the matrix. And we put an edge between, so here we'll put an edge between row I and column J, if and only if the weight Ij equals Ui plus Vj. So in our situation, as you see, I marked by purple those places where we have equality. So in the first row is the entry 5. So then row 1 is adjacent to column 5. In the second row is the entry 4. So row 2 is adjacent to column 4. In the third row is entrance 3. So we have row 3 adjacent to column 3. Fourth row is the position 5. So you have, so row 4. I think there's a mistake here. So this one is correct. And so we have row 3 with column 3, and then row 4 with column 5. And then the last one, row 5 with column 4. Something like this. Okay, so this is the equality graph. And now how does the algorithm proceed? Well, we ask, does this bipartite graph contain a perfect matching? If that was the case, so if this bipartite graph contain a perfect matching, then we would pick the edges in that perfect matching, and they would correspond to entries in the matrix Ij where the weight Ij equals Ui plus Vj. And that will guarantee that the weight of that transversal equals the cost of the cover, and that will be our maximum weight. However, in this situation, there is no perfect matching. And how can we say if there's no perfect matching? Well, by Hall's marriage theorem, that's the same as producing a subset. So this graph here, gamma UV, doesn't have a perfect matching. And I can produce a set of vertices S on the set of rows. Let's say it's the whole set, R1, R2, R3, R4, R5. So we have a set of 5 rows. whose neighborhood has it consists of just the columns C3, C4, C5. Therefore, if I call this S, the neighborhood of S has cardinality 5, which is bigger than 3, which is the cardinality of S. Okay. So what do we do in this situation? Well, what we'll do is we will decrease the entries in the, so here I assume all the entries are integers. So I will decrease the entries corresponding to the rows of S by 1, and I will increase the entries corresponding to the columns of S by the column of neighborhood of it. No, I wrote here something wrong, sorry. So the neighborhood of S is 3, which is less than 5, which is a cardinality of S, okay? And so what we do, we decrease the costs on the rows in S by 1, and we increase the weights for the columns in the neighborhood of S by 1. So if I were to keep it on the same picture here, so the way it would work is that the entry 5 would become 4, and so on. So these entries on the rows will go down by 1. So do them one at a time. So this is 4. This is 7. This is 4. And this is 7. And here the entries in the columns C3, C4, C5 would go up by 1. So this would be 1, 1. And now how does okay, so let's go back to the matrix. Now we can check again. We can, in the new matrix, we can try to mark again the positions where we have equality. So maybe it's easier if I do it on a different page here. So let's put it here, 2. So I have 4, 4, 7, 4, 7, and on the top I have 0, 0, 1, 1. And the entry in the matrix are the same, so 3, 1, 5, 4, 3, 5, 4, 7, 6, 8, 7, 2, 2, 1, 3, 4, 5, 6, 3, 2, 8, 7. So the matrix W is the same, and you see the cover weights have changed as they're written here. Now, to make it easier, sometimes you will see this written as follows. You can write, instead of the entries in the matrix as here the entries are, this is a matrix W with entries W, I, J. Here you can write the entries as being UI plus VJ minus WIJ for IJ between 1 and n. And what this does, it makes it easier where to find out the pairs IJ where you have equality of UI plus VJ equals WIJ. So let me rewrite these numbers here for 7, 7, and over here have 0, 0, 1, 1. And in the entries, you have, so the sum of the weights. So here we'll get a 1, here we'll get a 3. Here we'll get a 1, and a 0. And then on the second row, we have a 3, we have a 0, we have a 2, we have a 0 again here, and we have a 1. And then here we'll create a 0 here, we have a 1 here, another 0 here, we have a 1, and we have a big number here, 6. And then with a 4 there, we have 2, 3, 2, 1, and 0. And the last one, you have a 1, 4, 6, 0, and a 1. Okay. So in this situation, it's easier for us to figure out the places where we have edges, so we can mark them here. So all the zeros in this matrix. Okay, and now if we write down the bipartites with this new cover, I'll call it again U and UV. The bipartite, the equality graph will look as follows. The vertex set is the same, 5 rows and 5 columns. And now the edges are as follows. So you have, again, row 1 goes to column 5. Row 2 goes to column 2 and to column 4. Row 3 goes to column 1 and to column 3. Row 4 goes to column 5. And row 5 goes to column 4. Now, here it's a bit tricky to see if it has a perfect matching or not, but maybe if you stare at it long enough and you try to find one, it doesn't work. So then you can pick a subset of rows, let's say R1, R2, R4, R5. You can look at it through the perspective of the matrix, or you can look at it through the perspective of the graph here. So you have R1, R2, R4, R5. And what are the neighbors of these vertices? So you definitely have, so R1 is going to give us C5, R2 will give us C2 and C4. R4 gives us C5 again, and R5 gives us C4 again. So what we have is that the neighborhood of S consists of C2, C4, C5. So again, we have a set that violates Hall's condition. So we do the same thing. We increase UI by 1 for I in S, and we decrease Vj. No, the other way around. I'm sorry. So we decrease UI by 1 for I in S, and we increase Vj by 1 for J in the neighborhood of S. Okay, so let me do this over here on this on this picture on the left. So R1, this goes down by 1, so this is 3. This one also goes down by R2 goes down by 1. So that's 3. R3 stays the same. R4 goes down by 1. And R5 goes down by 1. So this is 6. And on the top, we have C2, C4, C5. So C2 becomes 1. C4 becomes 2. And C5 also becomes 2. Okay. And now, if we look at how this matrix to the right changes, so we will replace this part by 3, 3, 7, 3, 6, and the part on the top by 0, 1, 1, 2, 2. And now, if we look at the matrix that we obtain now, so let's let me erase here this matrix. So the entries in this new matrix UI plus Vj minus Wij are going to be the following. So in the first entry here, you get 3 plus 0 minus 3. This is a 0. Then we have 3 plus 1 minus 1. This is a 3. We have another 0 here. And then we have a 1. And we have another 0 here. So we created more zeros in the first row. In the second row, we get a 2. We get a 0 here. Get a 1. And a 0 here. And we have a 1. And then here we have a 0. 2. Have a 0. 2. And 7. Plus 2, yeah. And then the fourth row, we have a 1, 3, 1, 1, and a 0. And in the last row, we get a 0, 4, 5, a 0, and a 1. So we created much more zeros in this situation. And now, if we do the equality graph, we have extra edges here. I mean, you can do the equality graph as we did it on the bottom, but I guess the picture will get to be messy. So if we look at this matrix here on the top right corner, can we find a transversal of zeros? That's essentially the problem. And you can find some. I mean, there are several that you can pick, but you can pick one here, one here, one here, one here, and one here. So if we pick those entries and we pick them in the matrix here, here, and here, what we have is we have a transversal T, which consists of all these order pairs 1, 1, 2, 2, 3, 3, 4, 5, and 5, 4, with the property that for any ij in T, the weight of ij actually equals ui plus vj. So you see 3 equals 3 plus 0, 4 equals 3 plus 1, 8 equals 7 plus 1, 5 is 3 plus 2, and 8 is 6 plus 2. So that guarantees that T is maximum weight. And therefore we get that the maximum weight transversal for this problem is 3 plus 4 plus 8 plus 5 plus 8. And that is 28, I think. Okay, so that's how this this problem works. I hope this is clear. Now let's move on to other questions about matchings. Here's something about what happens in general graphs. So matchings. So in bipartite graphs, we discuss Hall's marriage theorem in several applications. But you can ask yourself, what happens in general graphs, non-bipartite graphs? So what happens in general graphs? The following is a result that takes care of this problem. So this is a theorem due to Bill Tutte, who's a famous graph theorist. He was born in England, but then he worked most of his life at the University of Waterloo in Canada. And this is the result that he proved. So if you have a connected graph, gamma has a perfect matching if and only if the following condition is satisfied. I will explain in a second what these notions mean. Number of odd components in gamma minus S is less than or equal than the cardinality of S for any S subset of vertices. So let's say gamma has vertex at V and that's it. Okay. So what do we mean by odd of gamma minus S? So if we have a graph, let's say gamma prime, graph odd of gamma prime equals the number of odd components of gamma prime. Now an odd component is just a component with an odd number of vertices. So if I have, for example, if my graph is this one, then odd here is 0. This graph is a one component, is a graph on 4 vertices, so there are no odd components. If I have this graph here, you have 3 components, one single vertex, which is cardinality 1, so that's odd. Then you have another component, this path on 3 vertices, which is also odd. And you have another component which has 4 vertices, so odd here is 2. Now, another situation that may happen is the following. So let's say we have a graph like this. So let's say this is our graph gamma, and S is the vertex here on the top. So gamma minus S is the graph obtained by deleting vertices, the vertices in S. Yes. So in our situation, if we delete the vertices in S, in this case being only one vertex, what do we get? We get a graph that has these 3 components. So in this situation, we have that odd of gamma minus S equals 3. So I hope this explains clearly what is the meaning of odd. And what do we mean by gamma minus S? Okay. So I won't prove this theorem, but I'll give you just the easy implication from it, showing that where this condition comes from. So again, let me state it here. If and only for any S in V, the number of odd components in gamma minus S is less than or equal than the cardinality of S. Okay. So I will just give you the implication from left to right. Okay. So this implication states that, you know, if the graph has a perfect matching, then this strange looking condition happens. So assume that gamma has a perfect matching. Let's call it M. Now, let's take our vertex set S. So take a vertex subset of vertices S. So let S be a subset of vertices. Okay. And now, when you delete S, you may create some components. The graph is connected. So when you delete S, you may create some components. So we can pile up those components into different parts. So here, these are the odd components. And on the other side, here, you have the even components. So again, even means that, okay, I have at least two vertices, or I have two or four, or so on. And odd can have something like this, and so on. Okay. Now, so let's say we have and here. So because we have a perfect matching, we look at each of these odd components. So we have a perfect matching in the graph. So every vertex of our graph is contained in one edge. In exactly one edge. Okay. Now, if we look at the component, one of these odd components, let's say the one here. So you see we have three vertices. So every vertex there is in some odd component. So let me see. No, every vertex there is in some edge, one edge of the perfect matching. So you could have, for example, this is an edge of a perfect matching, but no matter how you do it, there will always be one vertex because the component is odd, there will always be one vertex there for which the blue edge that contains it has to go between that odd component and S. Okay, not all the edges in there. So not all the edges inside that component, not so because in an odd component, yeah, you have an odd number of vertices, there will always be at least one vertex for which the blue edge that contains it has to go between that odd component and S. Okay, so similarly here, you could have these two edges that are in there, but then you are always left with some vertex for which that odd component has to go across. And now what you have is that for each odd component, you will have at least one edge, one blue edge going across into S. But because the blue edges form a perfect matching, the endpoints on the other side, these endpoints must be distinct. So if I had here, let's say T odd components, then I'm guaranteed that inside S, I will find T endpoints of these edges. So, but S could contain potentially more vertices. So what we end up with, cardinality of S is greater or equal than T, which equals this number of odd components in gamma minus S. So this argument cannot work on the even side, because you could have, for example, you could have this edge here, and so there are no blue edges going across. Or in this situation here, you could have, let's say, a blue edge here and a blue edge here, and you don't have a blue edge going between the even component and S. Okay, so this is the argument. Yeah, it's in the spirit of Hall's marriage theorem, but it's a different condition here. Okay. So with that, you can play around with graphs and so on. And so, for example, so I won't give you the proof of the other implication. This is more difficult. But you can play around, and for example, I can build a graph like this. So this is a graph gamma that is 3 regular. So every vertex has degree 3, and it has 16 vertices. But I claim that gamma has no perfect matching. And the way you prove it is by noticing that this condition here, you can call this a Tutte's condition, it fails. So there, we prove that there exists a subset of vertices S whose deletion creates more odd components than the cardinality of S. And here you can take S to be this vertex, and you have cardinality of S is 1. But the number of odd components in gamma minus S is 3, because deleting that S will create these 3 components, which are these 3, each being a graph on 5 vertices. So that's one way one can apply Tutte's theorem. Now, we've seen in this situation this problem where you have a deleted set of vertices and you can disconnect the graph and so on. So let's talk briefly about graph connectivity. So there are various ways that you can measure how connected the graph is. So let's say we have a graph gamma, which is a connected graph. So connected graph means that for any x and y in V, there exists a xy path. Now, so this is the definition. Now you can talk, if we take a subset of vertices before, this is called a disconnecting set or separating set. You have to specify what objects are there. So vertices, if gamma minus S is not connected. So the picture would be something of the following. You deleted these vertices in S. And you created this, the graph that that you create when you delete S. So S is the set of 3 vertices on the top. And the graph you create is this one here, but it's clear that you have 3 components, this one, this one, this one. So that would be a disconnecting set of vertices. Now, with vertices, we can define the vertex connectivity of gamma is defined as the smallest size of a disconnecting set of vertices. Now this works for, let's say, gamma. So in the case that gamma is connected, but gamma is non-complete graph. Why do I put non-complete graph here? Is because if the graph in the situation that gamma is the complete graph on n vertices, deleting any S subset of vertices with cardinality of S less than or equal than n minus 2 will not disconnect the graph. Actually, even if you delete n minus 1, what do you get? You get one single vertex. So for complete graphs, we kind of take it as by convention that the vertex connectivity, which we'll denote by kappa of Kn, is defined to be n minus 1. Okay. But if we take any graph gamma that is non-complete, that non-complete graph means that there exists some vertex x here, and there exists some vertex y here, such that there are no edges between them. And then it's easy to see that, for example, this subset of vertices, v minus xy, is a disconnecting set because it separates x from y. So in that case, we get that this vertex connectivity, which let's denote again, it's denoted by kappa of gamma. You get that if gamma is non-complete, it implies that vertex connectivity is at most n minus 2. Okay. And clearly, if the graph is connected, you need to delete at least one vertex, so it's greater or equal to 1, to disconnect the graph. Now, one can do something similar for edges. So we can define, so again, we have a graph gamma, and we can graph. We have f, a subset of edges is disconnecting, separating set of edges if gamma minus f is not connected. Okay. Now the picture is a bit different here. So let me give you some simple examples. Let's say we take a tree like this one. In this situation, any edge, so in a tree with n greater or equal to 2 vertices, any edge is a disconnecting set. Because if you delete, so if you take, say in any tree, if you take the endpoints of that edge x and y, and that edge is E, in that tree T, there exists a unique path, a unique xy path. And that path, it's exactly the edge. And if you delete it, if you do T minus E, that path is gone. And that means that there are no xy paths in T minus E. So the graph is disconnecting. You see, just deleting the edge doesn't break the graph just into components. You could break the graph in more components. In this situation, it breaks the graph into 4 components. But it depends. If you delete an edge incident with a leaf, it breaks the graph into 2 smaller trees. But generally, they could be more. Okay. So that's the situation here. Now here, we don't have a problem with the complete graph as we had with the vertices, because if I give you a complete graph, let's say in this case K4, if we delete the edges that contain one vertex, if we delete those edges, then we end up with one vertex, a single vertex on one side and a set of vertices on the other side. So you can always delete edges and disconnect a complete graph. Now, similarly as before, we can define the edge connectivity of gamma is the minimum cardinality of such f. Okay, so it's easy to see that, and this is denoted by k prime of gamma. And for the complete graph, it's easy to see that k prime of kn is n minus 1. The cheapest way to disconnect is just delete all the edges incident with the vertex. And for a tree, we did it already, k prime of t equals 1 if t is a tree with at least 2 vertices. Okay. But what's the relation in general between these two parameters? Well, so it turns out that there is a relation. Before I do that, let me state the result. I probably put it on a homework, leave it as an exercise. So proposition. So if gamma is a connected graph, if f is a subset, is a disconnecting subset of edges, and in addition, we want it to be minimal. So no subset of it has this property. Then f is of the form consists of all the edges between some subset of vertices S and its complement S complement. So what I'm saying is that there is S, a subset of vertices, such that F consists of all the edges X, Y, X in S and Y not in S. So if you're looking for smallest disconnecting subsets of edges, you might as well look at the ones that just go over all subset of vertices and look at the edges that separate them, that have one endpoint in that subset of vertices and the other endpoint across. Okay, so this would be now. Let's prove a theorem. So again, the same situation as before, gamma connected graph. And let's assume it's not complete. Then the vertex connectivity is greater or equal to 1, but it's less than or equal than the edge connectivity, and is less than or equal than the minimum degree. So some of these inequalities are easy. So the first one, it's this one. That's easy because gamma is connected. So you have to delete at least something. And this inequality is also easy because take a vertex x in gamma with the degree of x equals the minimum degree, and then just delete all the edges that are incident to that vertex, and you separate x from everybody else. So I'll just give you the proof of vertex connectivity is less than or equal than the edge connectivity. Okay. So for this, let's take S a subset of vertices in gamma such that the number of edges between S and S complement is the edge connectivity. Okay. Something like this. Okay, so the number of edges in between is the edge connectivity. Now we have two cases. So what I want to prove is that this number is bigger than the vertex connectivity. So case one is easy one in which every vertex in S is adjacent to every vertex in S complement. I mean, that could happen. I mean, there are many situations in which that can happen. For example, you can have one vertex here and two vertices here. So that's, that's a situation that could happen. And then, you have all kinds of edges in here and so on. But it could happen. Could have two vertices here and everything in here. And you have here all the edges in here and so on. So in that case, what happens is that K prime of gamma equals the cardinality of S as complement. But in this case, this is the cardinality of S times the cardinality of S complement, which is a large number. It's cardinality of S times n minus cardinality of S. And when is this minimized? This is minimized when S has cardinality 1. So this one here, it's not the right picture. Something like this. Okay. So in that case, this is greater or equal than n minus 1. So n is the number of vertices. But the vertex connectivity, we argued earlier, is at most n minus 1 if the graph is complete. So in this case, we're done. Now, case 2 is that there exists x in S and y in S complement such that x and y are not adjacent. So you'd have an x here and maybe a y here. Okay. So in that situation, what we do is we want to build some kind of disconnecting set. So what we do is we define the following. T is the following subset of vertices. Consists of the neighbors of x in S complement. So I'll just draw them as purple here. So this one here and this one here. And then union the vertices Z in S that have at least such that Z has at least one neighbor neighbor in S complement. So maybe our graph had some vertex like this. So you see some of those vertices don't have any neighbors in S complement, but in that case, so Z in S, but we want not in Z minus X. So in that case, this one and this one have at least one neighbor across. Okay. So the claim is that this set T is a disconnecting set of vertices. And that's not too hard to see because if you remove T from the graph, there's no way to get from X to Y. So it has no XY path. Okay, so in order for X to get to Y, it's either you jump from X to a neighbor of it across to one of these purple vertices, but these purple vertices now have been deleted, so you cannot do that. Or the other way is to walk from X to the golden vertices on the left-hand side and jump across, but those vertices have also been deleted. So there's no way to jump across if these vertices have been deleted. So this set T is a disconnecting set of vertices. And now the claim would follow if we can prove. So because it's a disconnecting set of vertices, that implies that the vertex connectivity of the graph is at most cardinality of T. Now, on the other hand, we have that K prime of gamma is the cardinality of the number of edges between S and S complement. So the claim is that that happens, that the number of vertices in T, you see here, this number of vertices in T is 4, is at most the number of edges. And how do you do that? Well, for each vertex in T, we create a edge in between S and S complement such that all these edges are disjoint, are distinct. So for the first vertex purple, we create this edge. For this outer purple neighbor of X, we create this edge. So for different neighbors, we'll have different edges. And now for each of the vertices that have a neighbor across, I can pick one of those neighbors and I can do an edge there. And here I can pick one of these neighbor of the golden vertex and make an edge over there. So that's how you prove that the cardinality of T is at most this number of edges, and that proves the result. So basically for any, so this is the inequality that one proves. And in general, there's no relation between these parameters. So these connectivities can behave differently. And one can prove, I'll leave this to you as an exercise, that for any A, B, and C, there exists a connected graph gamma with vertex connectivity being the small one, edge connectivity being the middle one, and minimum degree being C.